All right, we started last time with section 9.1. We're looking at sequences, and we were determining convergence or divergence, and I believe we had done example number 2. Yes. And so we did something that looked a lot like something you've done in Calc 1, even if it was a while ago. And we multiplied by the highest exponent in the denominator. That is, we used it as a fraction where it was the denominator. So the cubed, n cubed was our highest fraction, or our highest exponent. And we used the fraction 1 over n cubed to multiply the numerator and denominator. And then we were able to find limits that went to 0 and simplify that this is 3/2. Now, not every problem, of course, is a rational function, right? I mean, so the next example is not. The next example has factorials. So we have n minus 2 factorial over n factorial. And what we're trying to do is to find the limit of this as n goes to infinity. So we have n minus 2 factorial over n factorial. All right, so let's start with the denominator because it's just a simpler expression. Do you remember what n factorial means?
N times n minus 1 times n minus 2 times n minus 3 until you get to n minus n.
Yeah, so until we get to, I'll put 3, 2, 1 at the end,
Yep.
like that. Yeah, so that's my denominator. So if we think about the numerator in that same fashion, a lot of it matches up, right? So we have n minus 2 factorial, and we could write out a few more of them if you wish. I'll just write out one more. And then it's going to also do the same thing where it gets down to 3, 2, 1 at the end. And we see that we have the ability to reduce this expression quite a bit. So everything will cancel except what? I think it's just those two pieces, right? Everything else will cancel because they're factors. So we can reduce them. So we're left with one over n times n minus 1. Now, it's not really in the nicest, neatest, cleanest form, but it's much like what we had going on the top, right? We have something that's infinite in the denominator, right? N is going to infinity, so n minus 1 is also going to infinity. The entire denominator is going to infinity. And if you divide by something that's getting infinitely large, and the top's constant, this value will be what? 0, yeah. So this one's 0. It converges to 0. And again, we know it converges because we found its value. Okay, so those are two distinctly different types of problems. This one also is quite distinctly different. It's got a sign in it. We briefly talked about the fact that sign, bumps up and down last time. We were talking about it in another context. But it continually goes from -1 to +1, -1 to +1. It has no limit as n goes to infinity. But the denominator gets infinitely large. So you might think, okay, well, if you were to look at the graph for this bit, you might actually look at it, and it looks like it's tapering off to 0, and that should make sense. I'm bouncing up and down, but I'm dividing by something larger every time I bounce, right? All my bouncing actually keeps dividing by things, so it's going to sort of taper off. So you look something like this, right? And it is. That's what we're looking for. But again, that's very hand-wavy, right? We want to actually show this like legitimately with some mathematics to make it concrete. So we're going to write a little bit in here, and then we're going to actually write the solution for this on my next slide, which is below the next theorem for you. So we know sine of x oscillates from -1 to 1. But n approaches infinity in the denominator. So that is our denominator. Thus, we expect L to equal 0. why? Or how can we prove it, I guess would be another question. And we can do that using the theorem that's listed here next. Sorry, those lines end up looking kind of funky on my screen, but they're showing where you have underlined pieces. So if the limit as n goes to infinity of a sub n is L, and is the same as b sub n, and there exists an n in the natural numbers such that we've got these functions trapped, then for all n greater than n, the limit as n goes to infinity of c sub n is L. So here's what this is saying. If I take the limit of this one, and I take the limit of this one, and I get the same value, and I've got something sandwiched or squeezed in between, then clearly it must have the same value too. Right? I can't do something to two sides of the inequality that sandwiches it and the middle not do the same thing. So how do we show that? Well, we create this inequality to operate in the way that we want it to operate. So we know from what we said before that -1 is less than or equal to sine of n is less than or equal to 1, right? Of course we know that. And because n is positive, I can divide by all the pieces and the inequality will remain the same. Right? If n were negative, we'd reverse signs of inequalities, but it's positive, n's a natural number. So it's likewise true that I can write this way. Now that's very nice. It's very nice because this middle part right here is exactly what I'm looking for, sine n over n, right? And these outer two pieces, we know what happens to them as the limit goes to infinity, right? We've seen all those pieces, so we're actually able then to take the limit. So the limit of -1 over n is less than or equal to the limit. We should all have n goes to infinities. Of sine of n over n is less than or equal to the limit as n goes to infinity of 1 over n. But this one goes to 0, and this one goes to 0. Therefore, the limit as n goes to infinity of the sine of n over n is also 0. And we need to specify how we know that. We know that by the squeeze theorem. So when we apply a theorem, we're going to want to make sure we say so. This is our first theorem that we've applied. Okay, so we've so far had, so we should say it converges. Sorry, it converges to 0. So far we've had 3 sequences that we've dealt with and we found limits of. They've all converged because we've been able to find every single one of the limits. So I would be remiss if I didn't show you one that doesn't converge. So I'm going to spoil all the fun and tell you the next one's going to not converge. But take a look at it. Why should the next one not converge intuitively?
Numerator is greater power than the denominator?
Yeah, the numerator has a larger power than the denominator, right? That's going to cause the numerator to get infinitely large much, much faster, and that's going to cause a problem. So it's exactly right. And it's a rational function, so it's going to operate very much like the one that we did last time here, problem number 2, where we're going to look for that exponent and divide by it and all that kind of stuff. Okay, so we're going to treat it very much the same way. So let's take a look at this one just so you have an example somewhere in your notes of one that actually doesn't converge, because some of them won't. So we're going to take the limit as n goes to infinity of 4n squared plus 2 over n. So there's a couple of different ways you can do this. We could multiply by 1 over n. That would be okay. We can multiply by 1 over n squared, and that will be okay. All right, so you guys tell me which one you would intuit. Which one do you want to do?
1 over n.
1 over n. Okay, so we're going to go with 1 over n. And I'll show you what it looks like if we do 1 over n squared after that. So if we do 1 over n, remember you're writing down the limit until you take it. So the limit as n goes to infinity. And then I would have 4n plus 2 over n divided by 1. Okay? This piece right here, it goes to 0. Not that it really matters, but it does go to 0. But this piece right here is infinite, right? And we're dividing by 1 as a constant. So this one is going to infinity. If you have infinity plus 0, so to speak, this is infinite. And therefore it diverges. If you didn't do it this way and you were looking at it by 1 over n squared, so let me just show you the computational part of it without writing all the limit part of it down. So if we were doing this 1 over n squared here, we would get 4 plus 2 over n squared over 1 over n, like that. And as we take a limit, this one goes to 0, and this denominator, which doesn't affect anything, that's fine. So I end up with just getting 4 on top. But this denominator going to 0 means I basically have 4 divided by 0. When you divide by 0, you get infinity, right? That's the plan. So this one ends up becoming, this one also approaches 0, and when we divide by something infinitely small, we get infinity. So you get an infinity from that way. So either one of them, whichever perspective you come from, you get that it diverges. Okay, is that all good? Okay, we've got one more transcendental function to look at. Natural log. Okay. So this one's tricky. There's no rational thing you can do with it. We don't have anything that we can handle where we can sandwich it in between. The squeeze theorem is not going to work for us because the log function's not trapped between values, right? So when we're looking at this one, we have kind of a new problem that's occurring. And since it's on the page right afterwards, you can see exactly where we're heading, is that we're going to take a look at L'Hopital's rule. So have you seen L'Hopital's rule before? Great, you should have. So L'Hopital's rule tells us what happens when we can't find the limit of a particular function. And what it actually is saying is that we're able to take the derivative of the top and the bottom and use those values instead. So we'll read through it together. So suppose that f and g are functions that are differentiable on an open interval. This is L'Hopital's rule straight out of the book from before, and it applies to sequences just like it applies to functions. So we're just going to use the function definition, but it applies to sequences. Differentiable on an open interval AB containing C, except possibly C itself, as long as the derivative of the G prime is not, or the derivative G prime is not equal to 0, except possibly at C itself. If the limit of f of x over g of x as x approaches C produces the indeterminate form 0 over 0, then the limit of f of x over g of x is equal to the limit of f prime of x. Off my screen. Let me scoot this over just a little bit. Here we go. Over g prime of x. And we can repeat that process. Let's suppose that still doesn't work. That still gives us a 0 over 0. Okay, well then we'll take the second derivative on top, second derivative on bottom. Right? We can do this sort of indefinitely until it actually helps us, or until we decide this isn't going to help me. And there are some functions for which it doesn't help you, of course. The result also applies when the limit of f of x over g of x as x approaches c produces any one of the indeterminate forms. So we already said 0 over 0, but I'll include it. It also, will work when we have infinity over infinity. That's the one our problem is going to have. And then you can also put positives or negatives anywhere. So like if you had negative infinity over infinity, or infinity over negative infinity. So negative doesn't change anything. So I'm going to go back up then to problem number 6, and we're actually going to use L'Hopital's rule to find this limit. So I'm actually finding the limit as n goes to infinity of the natural log of n cubed over 2n. And you have to stop and check and make sure it really fits L'Hopital's rule before you just plow through using it. Right? Does it give you infinity over infinity or 0 over 0? Yeah, it would give us infinity over infinity on this one. So L'Hopital's rule applies. So this will equal the limit as n goes to infinity of the derivative. However, I think probably before we do that, it might be helpful. It's not the only option, but it might be helpful to apply a property of logs. Can anyone see a property of logs that would be helpful right now? Yeah?
Pull the 3 to the front of the equation.
Yeah. If I take a derivative right now, it's not that you guys can't handle it, but you're going to have to use a chain rule, right, on top. If I pull the 3 from the exponent of the log part that's interior to the log to the front, then I'm not going to have to use a chain rule. It's just going to make the process cleaner, have less going on when we're done. So the first thing I'm actually going to do is to simplify with a property of logs by doing that. What was it, 2n? Now, that's not L'Hopital's rule yet, right? But now we're still ready for L'Hopital's rule. It's still infinity over infinity, by the way. So that didn't change the expression. It just changed the way it looks, right? It's like changing 2/4 to 1/2. That didn't change the number. You just changed the way it looked. So this is the same value on top, so I have the same limit at the moment. And I still have the infinity over infinity. So what's the derivative of 3 natural log of n? 3 over n. That's right. 3 over n. Uh-huh. And what's the derivative of 2n? 2. So if we simplify, clean this up just a tiny bit, we would have 3 over 2n. Does that look right? Okay. Can I put the infinity, conceptually, can I make n infinite now and get a value or not get a value? I can. I don't end up with an indeterminate form still, is what I'm trying to get at. There's no infinity over infinity or 0 over 0 at this point. We actually have a value. So what will happen now as n goes to infinity? It's going to approach 0. Infinite on bottom becomes 0. So this limit is 0, which means that this will converge to 0. Okay, we need a little bit more vocabulary before we're able to do the last bits of the problems. And so we're going to talk about things being monotonic, bounded, and what those are going to do for us. And the primary reason we're talking about them is because they show up in the conditions at the beginning of a lot of the theorems that are going to follow in the later sections of Chapter 9. So we're going to see them say things like, as long as these functions, these sequences have these conditions, then this will apply. So we need to know what those conditions are, and we need to know how to check for them. So our first one we're going to look at is monotonic. So monotonic is a word to describe increasing and decreasing at the same time. Okay? So it's monotonic when it's either non-decreasing or non-increasing. So this is kind of like when you say something's positive or negative and somebody's like, well, what about 0? And you're like, well, positive or 0, right? It's got this condition, and so you see these greater than or equal to signs, these less than or equal to signs showing up. So non-decreasing means that it gets bigger or stays the same. Non-increasing means that it gets smaller or it stays the same. And it doesn't have to do it the whole time. So in theory, you could have something that sometimes stays the same and then sometimes it decreases or increases, and it still fit in that category, right? So something like, make sure I get my order right, I did non-decreasing first. So if I had 0, and then I had 0, and then it went up to 1, and then it went up to 2, and then it went to 2 a couple of times, right? So it could decrease, in this case, right, it still fits the description that's there, and that would be considered non-decreasing. Okay, it's increasing or staying the same as it goes. So that's monotonic. And the other one is bounded. So a sequence is bounded above when there is a real number m such that the sequence a sub n is lower than the bound for all n. So picture in your mind an asymptote, horizontal one. Horizontal asymptote that creates this boundary that you can't extend beyond. Right? That's bounded above. Bounded below is exactly the same thing. It's just from the bottom side, right? You can't go below that horizontal asymptote feature. And then we call it bounded when it has both of those features.
So like sine would be bounded between 1 and negative 1?
Exactly. Sine would be a bounded function, whereas, just like y equal x squared wouldn't be. Right? However, y equal x squared would be bounded below. There's not an asymptote, but it is bounded below. There is a point below which it does not go, right? So that one would be bound below, just not bounded in general. Okay, so there's kind of a trick in showing how to prove something is bounded, and so that's what I'm going to show you on this next example. Which turn? Okay, so we're going to determine if the sequence is monotonic and or bounded, and then we're going to confirm it graphically, so we'll draw a graph of it when we're done. This is not an unfamiliar type of an equation. If you think of it in terms of x minus 1 over x plus 1, it's a rational function. It's got a hole in it somewhere. It's got some asymptotes in there, right? That's what we're looking at. And so we're going to determine first if it is monotonic. Okay. So what I'd like for us to first do is to write down what a sub n plus 1 would be. Okay, so determining if something is monotonic is determining what happens in the next term, and the next term, and the next term. So we're just going to write down a general next term. So if our first term is a sub n, the next one's a sub n plus 1. So we have n plus 1, and then minus my 1, and n plus 1, and plus my 1. Okay, so first so good? So I have n over n plus 2.
Isn't
Did I write something wrong?
it's n minus 1, right?
We're replacing the n's in each case with n plus 1.
Oh, sorry.
Yeah, that's what we're doing. So this is the n is the sort of the variable component, the sequencing component, and down here it's n plus 1 that we're replacing it with. Yeah. Okay, so this is the trick. This is the part that you wouldn't necessarily think, oh, I should do this next. What we're going to do is we're going to take a ratio of a sub n plus 1 and a sub n. We know both of them, so we can do that, and you'll see why we'll want to here in a minute. So I have n over n plus 2, and I have n minus 1 over n plus 1. And we're going to flip them, simplify them. So n over n plus 2 times n plus 1 over n minus 1. And this is going to create n squared plus n over n squared plus n minus 2. Okay, so that's the first trick, just writing this ratio, which we haven't established why we did it just yet, but we will. Okay. The next thing is that we're going to do kind of a funny thing, and we're going to use kind of a partial fraction representation. So I'm going to take my n squared plus 2, or n squared plus n, and I'm going to subtract 2 from it so that it matches the denominator. Now, obviously, you can't just go subtracting 2 from something. That's not appropriate. I have to balance it, so I'm going to add a 2 back in as well, in its own little bitty fraction over here, n squared plus n minus 2. So I've subtracted n and I've added in. I've subtracted 2 and I've added 2 into the situation. But in doing so, what did I create at the first fraction? The number 1. Okay, that's the number 1. So this is 1 plus, and then right now, what I want you to recognize is what the value is. I don't mean specifically, but what I want you to recognize is this value positive, negative, or is it something sort of like it goes back and forth? What kind of number do I have there?
Should be positive.
Should be positive, right? Remember, n is a positive number. So I'm squaring something positive, I'm adding something else positive to it. As long as it's bigger than 2, right? As long as my n is not 1. If n is 1, I've got a problem, because I'm going to get a 0 in the denominator. But as long as n is bigger than 1, this is going to actually give me a positive number on bottom. And when I take my positive number on top and divide by the positive number on bottom, I'm still going to get a positive number. Agreed? So this is something positive. So this is something greater than 0. Why does it matter? Well, what happens here then is that this just told me that the value here on the right-hand side is actually bigger than 1. So I'm going to write this down here. I've left them off all the way along. A sub n plus 1 over a sub n is actually greater than the number 1 because the right-hand side is bigger than 1. So a sub n plus 1 over a sub n is bigger than 1. And if I multiply a sub n to the other side, or to both sides, I have an inequality that shows the relationship between sequential terms. I know that a sub n plus 1 is bigger than a sub n. Always. And likewise, if I had found that it was less than n, or I'm sorry, less than a sub n, right? Either way, that proves that it's monotonic. I just proved that if I have a sub 7, it's bigger than a sub 6. If I had a sub 10, it's bigger than a sub 9. And so since I can do this for any term, and because I did it in general, right, for any nth term, this proves that it's monotonic. So I have a monotonic sequence. The next thing I'm supposed to be showing is that it's bounded, right? Specifically, this one's increasing, monotonic and increasing. So the next thing is bounded. So, whoops. When n equals 1, a sub 1, okay, I know my sequence is always increasing. Let me pause there first. Since it's always increasing, then the smallest value that's going to exist is going to be the first one, because the next one's always going to be bigger. So I'm establishing what the bound is on the first one. That's going to be my bound below. Everything's going to get bigger after that. So a sub 1 would be 0. Well, I'll put it in. 1 minus 1 over 1 plus 1. So I have 0 over 2, or 0. So it's bounded below by 0. And that's because it's increasing. I didn't ever actually write that on my screen, but we talked about it. 0 is the first term. It's going to get bigger after that. That's my lowest value. It's bounded below by 0. All right, so secondly then, let's see how I want to start this. A sub n is n minus 1 over n plus 1. This is actually less than n over n plus 1. Why? Why did that make it bigger?
You're not subtracting.
Yeah, I'm not subtracting one on top. The numerator simply got smaller, so the whole fraction itself is going to get bigger, right? Yeah, so that's bigger. And then I'm going to do the same sort of thing on bottom. I have n over n on bottom. So if I take the bottom plus 1 away, why is that going to make it something bigger? I'm not dividing by as much, right? If I divide by 3 kids in my household with the cake, they're going to get more cake than if I have all 5 kids there at the same time, right? Divided by something smaller, so it's getting bigger. This is actually equal to 1. So a sub n is always less than 1. So it's bounded above by 1. So it's bounded below by 0, bounded by above by 1, thus it's bounded. And if you were to grab calculator, check the graph of this thing, and we really only care about the graph of it right after the number 1, but I'll draw a little bit more of it just to give you some context. The graph looks something like this. And it crosses here at 0, and then it bounds up like this. It's bounded above right there. So this is the graph of the function associated with it, right? The graph of this would actually just be individual discrete points. But the graph of the function itself has a 0 right here, and then this asymptote right here is at 1. So you can confirm your suspicions and that your work was in the right direction. Any questions on that? All right.